Similarly, if you want to calculate the line voltage between line C and A, that would be the VCN minus VAN. So VCN minus VAN. This is the rotation. A, B, B, C, C, A. It's easier for us to remember the rotation. The windings can be represented as a U, V, W, X, Y, Z. But we will try to focus on A, B, C rotation to make sure we practice the equation appropriately. Now, these little bars, if you are wondering what they are vector representation. That means each has a particular direction. If your voltages have angle and the magnitude, you do know it can be drawn with a particular direction and angle. So these bars represent the vector representation of the voltages, phase or neutral voltages. Now, these are the simple three equations, but you might be thinking, if I want to calculate VAB, the line voltage, I need to have the value of VAN and VBN. From where would I get these values? Well, that depends on to the question. If the question gives you the phase voltages, VAN, VBN, then it is a simple subtraction in complex form. We are going to practice this. I would appreciate your patience. If we want to draw it on the phasor diagram, it is also possible to draw because these are all vector representation. So you have the three phase voltages, VAN. We considered it as a reference point. Reference means the VAN, whatever the magnitude is, has 0 degree angle. In this way, VBN would have the minus 120 degree, VCN would have the plus 120 degree. If I want to calculate the line voltage using phasor diagram, so in the previous part it was using mathematics, but you can also calculate the line voltage VAB on phasor diagram. So this is the method where we draw the phasor diagram for the voltages first by knowing the angles, 0 degree, minus 120 degree, plus 120 degree. The length of the line is dependent on to your scale. Let's suppose 1 centimeter is equals to 60 volts. Whatever the voltage is, we can draw it on phasor diagram. That's the fundamental. Now, in order for us to draw or calculate the line voltage from the phasor diagram, we need to know the equation. So, VAN minus VBN. It means VAN is positive, VBN is negative. Using phasor rotations, if this is the VBN which is positive, then the negative would be having the same angle, same length, but opposite in direction. So we can draw minus VBN by just projecting the same length of the line, same angle, but in opposite direction. In this way, you can get minus VBN. You already have VAN. Now we can actually add two lines on phasor diagram using the fundamental mathematical principles. If I want to add two lines, one line which is minus VBN, another line which is plus VAN, I use the word add because it's the same thing. We can always add two lines on phasor diagram like this, but you need to draw the imaginary lines by completing a parallelogram. The parallelogram, which means we draw the imaginary line. Let's start from minus VBN. We draw the imaginary line by following the angle of this line, a straight line, would be the angle of VAN. So this line has infinite length but having the angle of VAN. Similarly, if we want to draw the imaginary line at VAN, the angle of this line VAN would have the same angle of VBN, which is minus VBN. At the point of intersection, like I said, it is infinite line, which means you can draw this line as bigger as you possible. At the point of intersection, we can draw the line pointing towards the origin, 0 point. The length of this line and the angle with respect to 0, you can convert the length into the voltages using the particular scale that you have already started at the first place. And the angle you can measure using protractor. In this way, without using any calculator, we can calculate the line voltage VAB using a phasor diagram. We will probably not be practicing much on these things because that requires more time to practice. But I will show you with using my example question to demonstrate these concepts as much as I can. But basically, the purpose of this phasor diagram was to calculate the line voltage VAB from VAN and VBN using phasor diagram. Of course, we are using the mathematical representation here. So VAN plus minus VBN, which is the same thing, VAN minus VBN. This is the hypothetical diagram that does not show any scales. So, but we do understand that we need to draw any of the length of the line with the particular scales of the voltages. This applies to the voltage at the moment, but of course, we can draw the currents as well. Since in the star system, the line currents are equal to the phase currents, so there will not be any complexity in drawing the currents in the star connected system. Now, here now let's practice the example question number 1. Just want to make sure it's working. Yeah. So balanced star connected system example question number 1. We are going to practice the equations and to see how we are going to solve this type of question. So let's read the question first. The adjacent, which is on the left hand side, star connected impedances. So we have three impedances, the loads connected to three lines A, B, C. Those impedances are having the same value. Z is equals to 40 plus J 30 ohms. And all impedances are equal. That means it is the balanced star connected system, three-phase system. The adjacent star connected impedances are supplied from a 415 volts. What type of voltage it is? Is it a line voltage, phase voltage? What angle? So we are going to look at the circuit here. In this circuit diagram, it says the 415 voltage is the magnitude between line A and line B. We don't know the angles yet. That's what we have to calculate. Now, 415 volts is the line voltage. Supply frequency 50 Hertz, three-phase supply and neutral system, which means a star connection would always have a three line voltages and a neutral. In the first part, it says calculate the phase voltages. Now, the first thing that would come into your mind would be that is easier because line voltage is equals to square root 3 times the phase voltage. So the phase voltage will be equals to line voltage divided by square root 3. So if we do that, 415 divided by square root 3, this gives us approximately 240 volts. So 240 volts is the phase voltage. But the question is asking you, calculate the phase voltages, means all three possible phase voltages. But in order for us to calculate all three possible phase voltages, which would have the same magnitude 240 volts, but the angles would be different. In order for us to predict the angle, the question must provide us the reference point. Which one is the reference point? So in this question it says using the phase voltage VAN as a reference. Now we are going to look at this blue text only. But this is the data. You can calculate the phase voltage using this fundamental equation. VL is equal to square root 3 times the phase voltage. And this gives you phase voltage magnitude. Because the